This video is on section 9.1 notes, and in your textbook, if you look, you can see that section 9.1 is called Solving Linear Systems Using Matrices, and that's what I called, that's essentially what I called our last section. And so we're actually doing the same thing in the last section that I went over with you guys, where I kind of did like a mixture of a few different sections together. And showed you how to use matrices to solve systems. And today we're going to do the same thing again, but we're going to do a specific method. And so I titled this section after the method that this section is based on. So it's the Gaussian elimination method. All right, so first thing that you'll do when you work with a problem is you'll take the system and think of it in terms of the matrices that we were talking about in the last section. So we have the coefficient matrix for this system and the variable matrix, and then the constant matrix. And what we do when we do the Gaussian elimination method is we take these matrices, there's three of them, and we just write it as one augmented matrix instead, where we kind of ignore the variable matrix and we just write the coefficient matrix and then a line and then the constant matrix. So 2, 1, 1, -1, 5, 4. So that's an augmented matrix. So the first thing we're going to do is just practice writing a couple augmented matrices for a few different systems of equations. So for this first one, we have a system where it's not written in standard form. You'll notice this system was in standard form up here. So first thing we need to do is rewrite this system so that the x's and y's are together on the left. X minus y for that first equation equals 3. For the second equation, I'll add the x to the other side. X plus y equals 4. And then the augmented matrix would look like that. For this matrix, we have 3 equations and 3 variables. The second equation is missing the y variable, so we're going to put a 0 in for that one. So 1, 2, -1, 1, 2, 0, 3. 3, -2, 1, 0. Okay. And then over here we have 2 equations, but in terms of 3 variables. So we're going to have to put some zeros in here. And I'll be honest, I don't know when an augmented matrix of 2 equations and 3 variables would really be helpful. I feel like that's too many unknowns. But if you run into it, at least you'll know how to write the augmented matrix. So you can see with this one, for that first equation, I put a 0 in for z because it's missing the z value. And then for that second equation, I put a 0 in for x because it's missing the x value. I didn't do a third equation because there wasn't one. All right, next example gives you an augmented matrix, and we're going to write the system. So this has 3 columns, 3 rows, so we've got 3 variables and 3 equations. So we're going to do x, y, z, 2x plus 5y plus z equals 2, -3x, I don't need the y, plus 4z equals -1, 4x minus 5y plus 2z equals 3. Okay, so writing in an augmented matrix or writing an augmented matrix as a system, pretty simple. Okay, so now we're going to move on to the Gaussian elimination method. This method is not easier than what I showed you in the previous section. So the previous section is going to be your preferred method if you are able to do it. The Gaussian elimination method is simply part of what we're required to teach, and so I'm going to teach it to you. But also, if you continue on in mathematics and you ever study linear algebra uses a lot more with matrices, and it would be helpful for you to have become familiar with this. There might be other contexts where the method we used before wasn't possible, but the Gaussian elimination method is. And then we also did talk about when you have inverses, when you're using inverse matrices to solve something, not every matrix has an inverse, and not every matrix is invertible. You might have a determinant that's 0, and so you can't find the inverse of it because the formula says 1 divided by determinant. So this could be useful in a variety of circumstances. Anyway, so the Gaussian elimination method uses row operations. And when I say row operations, there's a few different things I mean. So one is that you could interchange 2 rows of the matrix. You could trade them, row 1 and row 2. You could make them switch. You can multiply every entry in a row by the same number. So you could take row 2 and multiply every number in row 2 by 2. Or take row 3 and multiply every number in row 3 by a negative. And you can add to a row a non-zero multiple of another row. So what we could do is we could take row 3 and multiply it by 2. And then once we've done that, we could add it to row 1. So those are the different row operations we can do, and they'll be beneficial, as you'll see in a second. So when you're using the Gaussian elimination method, your goal is to get an augmented matrix that corresponds to a system whose solution is obvious. So the solution is obvious if you have your coefficients as the identity matrix and your constants as numbers. Because remember, the augmented matrix represents the coefficients times the variables, but we don't write those down. So this vertical line, you could think of the vertical line as kind of representing the variables, equals the constants. So if we have the identity matrix times the variables equals numbers that are constants, then we have the solution. So it's our goal to make our augmented matrix on the left side have the identity, because then on the right side we have the answers. All right, so the method we're going to use to do this is the Gaussian elimination method, and we are going to convert the coefficient matrix within the augmented matrix into the identity matrix. We're going to make it 1s and 0s using row operations. And then once we've done that, then the numbers on the right are going to be our solution to our system of equations. Okay, so I have a couple examples we're going to go through, and I'm going to give you a lot of support with the first one, and then as we go through, I'll start taking some of those supports away. So the first thing we're going to do here, we have a system of equations, and the first thing we do is we write the augmented matrix for the system. So I've got 2, -4, 16, 3, 1, 3. All right, and it says to get a 1 in the first position on the diagonal, because remember our goal is to have this identity. Get a 1 in the first position on the diagonal, and to do that, to get a 1 right here where there's a 2, we're going to take this entire first row and we're going to multiply it by 1/2. We're going to cut all those numbers in half. So take half of row 1 and use that to replace row 1. So half, 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 that's going to give me 1, -2, 8. And row 2 is going to stay the same. So you can read this as half of row 1 becomes row 1. That's how you can read this, okay? And this is important because this is kind of like your key. It's telling you what's happening. Okay, so now next down here, we want to have a 0 right here because that's what the identity matrix does. It has a 0 right there. So to get a 0 down there, we're going to take row 1 and we're going to multiply each of these entries by -3, because if I have a -3 right here and a +3 right there, if I then add the 2 rows together, they will 0 out. So I'm going to take row 1 and multiply by -3 and then add the result to row 2. So row 1 multiplied by -3 is going to be -3, +6, -24. I'm going to take that and add it to row 2, so -3 times row 1 plus row 2, 3, 1, 3.
Unknown caller.
Sorry about that. And that's going to give me my row 2. 0, 7, -21. Now, I'm not changing anything about row 1, so I'm just going to take row 1 from the previous augmented matrix and I'm going to copy it down. Okay, now my next goal is to get a 1 here on the diagonal. So if this is a 7, I can multiply the entire row by 1/7, and that will make this 7 become a 1. So 0, 7 times 1/7 is 1. -21 times 1/7 is -3. So I took row 2, I multiplied it by 1/7, and I replaced row 2 with all of those numbers. Row 1 doesn't need to change, so I'm going to write row 1 exactly the same way. All right, on the next page. Now my goal is to finish getting the identity matrix right here. So this -2 needs to become a 0. To make it become a 0, I want to add a +2 to that. So I'm going to take row 2, I'm going to multiply it by +2 because then +2 and -2 will cancel out. So I'm going to take row 2, 0, 1, and -3, and I'm going to multiply by 2. So 0, 2, and -6. And I'm going to take 2 times row 2 and add it to row 1. 1, -2, 8. So 1, 0, 2. And now this can replace row 1. 1, 0, 2. Row 2 didn't need to change, it was perfect, so we'll just write row 2 in there. So at this point, I have 1 for x is 2. I have 1 for y is -3. So my solution is 2, -3. Okay, so I know that sounded crazy, so let's try it again. We're going to use row operations. We're going to use the Gaussian elimination method to solve the system. So the first thing we do is we write the augmented matrix for the system. 2, -1, 7, 1, 3, 14. Okay, now our goal, remember, is to get the identity matrix here. And the pattern that you might have noticed is that what they did first is they got a 1 in this position, and then they got a 0 underneath it. Then they got a 1 in this position, and then they got a 0 above it. And that's how we're always going to go when we do a 2x2 matrix. We're going to do 1, 0, 1, 0. Okay? So we have to get a 1 in the first position on the diagonal. We need a 1 right here in the upper corner. Now you have 2 ways to do that. We could take the first line and multiply it by 1/2. That would give us a 1 in this upper left corner. But the other thing we can do is we can just take this equation that already has a 1 there, and we can write this equation first. So that's what I'm going to go ahead and do on this one, because I don't have to multiply everything by 1/2 if I already have an equation that has a 1 in it. So I'm going to write 1, 3, 14, 2, -1, 7. And if I write the instructions, that little notation that shows what I did, I'm going to say that row 2 became row 1, and row 1 became row 2. Okay? All right, my next goal is to get a 0 right here where there's a 2. And to do that, I need to have a -2 to cancel it out. So I'm going to take row 1 and multiply it by -2. -2 times row 1. So that's going to give me a -2 in this position. And then when I add these two together, the -2 and the +2 are going to cancel out. So I'm going to do -2 times row 1, and I'm going to add it to row 2. And when I get the result of that, I'm going to write that result in for row 2. Okay, so my goal here is to get a 0 where this 2 is, and so row 2 is what's going to be replaced. So -2 times row 1 is 1 times -2 is -2, 3 times -2 is -6, 14 times -2 is -28. Okay, and then I add that to row 2. And I get 0, -7, -21. And so this becomes my new row 2. 0, -7, -21. My row 1 didn't need to change, so I'm just going to copy it exactly as it is. All right, so I had the 1, the 0 beneath it. Now this is going to become a 1. So to make this down here, to make that -7 become a 1, I have to multiply by the fraction 1/7. That makes it a 1, but I need it to be a +1. So I'm going to multiply that row by -1/7. So row 2 multiplied by -1/7. -1/7 times row 2 is going to become row 2. So 0 times -1/7 is 0. -7 times -1/7 is 1. -21 times -1/7 is 3. And then row 1 didn't have to change at all, so I'm just going to rewrite that one in here. Okay? And now that I've done the other one, I have to do a 0 right here. So to cancel out a +3, I need a -3 to add to that +3 to cancel it out. So this is going to have to multiply by -3. Row 2 is going to have to multiply by -3 and then be added to that +3 to cancel it out. So row 2 multiplied by -3 plus the +3 is what's going to make that cancel out and give a 0 in that space. And -3 times row 2 plus row 1 is going to replace my row 1. So I'm going to take row 2, 0, 1, and 3, and I'm going to multiply by -3. So 0 times -3 is 0. 1 times -3 is -3. 3 times -3 is -9. And I'm adding row 1 to that. So 1, 3, and 14. And I get 1, 0, and 5. And that replaces my row 1. And then row 2 didn't need to change, so I can just copy down row 2. And my solution is that x is 5, y is 3. So this solution is 5, 3. All right, so the next page of notes has a list that kind of talks you through these steps. So it says, if necessary, interchange the first and second row so that you begin with a non-zero entry. You can't have a 0 in the first position. You have to have something that you can turn into a 1. So we start by getting a 1 in the first position on the diagonal by multiplying that by the reciprocal. So we didn't do that in the second example because it already had a 1 there, but we did do that in the first example. Because in the first example, we had a 2, and so in the first example, we multiplied by 1/2. Okay, so we multiplied by the reciprocal. All right, then it says to add an appropriate multiple of R1 to R2 to get a 0. So this is where we said, okay, we needed to get rid of a 2, so we did negative 2 times R1. And that's going to get rid of a 2, and that gave us a 0. Then it says the next step is to get a 1 in the second position on the diagonal by multiplying R2 by the reciprocal. So negative 7 is what we needed to get a 1 for, and so we multiplied by the reciprocal of negative 7, which is negative 1/7, and that gave us a 1 there. Then it says to add an appropriate multiple of R2 to get a 0 above that second 1. So we needed to cancel out a positive 3, so the multiple of R2 was a negative 3. And that gave us 0 in that position. And then once we did that, we could see the unique solution, 5, 3, and that's the solution to the system. Okay, so all you really need to do are follow through these steps, which is what we did here. Okay, so we're gonna finish these notes. It says no solutions and infinitely many solutions. We know that that can happen in a system, and we just want to see if we're doing the Gaussian elimination method, what is that going to look like? So we're going to go ahead and start looking at this system right here. I'm going to have to rewrite it. The first equation, x minus y equals 3. The second equation, I'm going to subtract the 2x over, negative 2x plus 2y equals 5. Okay, so my first step is to write the matrix for the system. 1, negative 1, 3, negative 2, positive 2, 5. So our first step is to get a 1 in the first position of the diagonal, and this augmented matrix already has that. So I'm just going to copy this down. My first step is done. Okay, then I need a 0 right underneath that 1. So to cancel out with a negative 2 down here, I need a positive 2 to cancel it out. So I'm going to do positive 2 times the first row plus the second row. Positive 2 times the first row plus the second row, and it's going to replace the second row because I want the 0 in the second row position. So it's going to replace R2. Okay, so the first row times 2, 1 times 2 is 2, negative 1 times 2 is negative 2, 3 times 2 is 6. I'm adding that to the second row. I get 0, 0, 11. And so that's my second row. My first row didn't need to change. It already had a 1 in the correct place. And what you might notice here is that this would be a little bit strange because our first position represents an X, our second position represents a Y. And so what we have here is that the X's and Y's have disappeared. We have no variables. That equals 11. So we would end up with an equation where 0 equals 11, and that's not true. That's not possible. And we don't have a way to introduce a 1 here because we can only multiply by numbers. We can multiply by the reciprocal, we can multiply by a scalar, but we can't add a number in. So this gives us the equation 0 equals 11, which is not true. And so that means this is a situation where there is no solution. This is what it looks like if you have a system with two parallel lines. They have different y-intercepts, but their slopes are the same, so they're never going to cross. All right, now that we've seen a no solution problem, we're going to look at a problem that has infinitely many solutions. So for this one, I'm going to go ahead and start off by writing my augmented matrix. And hopefully in a situation like this, you might notice already that your two equations have kind of a special relationship. I can see that if I were to take my first row and double it, I get my second row. And so looking at those already, I can tell, oh, those equations are the same. The second equation is like a scalar multiple of the first equation. Let me write this off to the side. R2 is double R1. And so what my job is here is to show that in this situation, we're not going to end up with 0 equals 11 like we did in the previous situation. We're not going to end up with something that is not true. We're going to end up with 0 equals 0, which is a situation that is always true because the two lines are the same. They're on top of each other. So every single point on the line is a point of intersection. So what I'm going to do is I'm going to take, instead of doing what I normally do and getting a 1 and trying to get the diagonals like I did previously, I'm just going to try to get a 0 all the way across the bottom. And the way I'm going to do that is I'm going to take the first row and I'm going to multiply it by -2. So -2 times the first row, and I'm going to add it to the second row. And what you'll see is if I take this first row and multiply it by -2, 2 times -2 is -4, 1 times -2 is -2, 4 times -2 is -8. If I take -2 times the first row and I add it to the second row, then I can replace the second row with these zeros. So I'm going to replace row 2. So my new augmented matrix is 2, 1, 4, and then 0, 0, 0. And we end up with 0 equals 0, which is a true statement. And when you have that true statement, it means you have infinitely many solutions, like I said before. The two lines are on top of each other and they intersect at every single point on the line. So now if I want to write a formula for how you could get points that are on that line, I'm going to write them in terms of the equation of that line. So I can write it two ways. I can say the x-coordinate is just x and then write a formula for the y-coordinate, or I can say the y-coordinate is y and write a formula for the x-coordinate. So here I wrote x is x, and then for a formula for the y-coordinate, I'm just going to isolate the y. So get that y alone, subtract the 2x to the other side, and I get y equals -2x plus 4. So if I wanted to know what any of the solutions were, I could pick a number to plug in for x, like I could plug in 1, and then I could plug in that same number and find the corresponding y-coordinate. So that would be the point 1, 2 would be a solution that would work. There's infinitely many solutions, so I could plug in any x value that I wanted and just keep spitting out more and more points. I could have done the same thing and just solved for x instead of solved for y, and then I would have had another point that was in terms of y instead. So it doesn't matter how you do it. I'm guessing that writing it in terms of x is probably more common, but truly either is fine. Okay, so we're going to finish off these notes by using the Gaussian elimination method for a 3x3 system. So a system in 3 variables that gives you 3 equations. And so to understand how to apply the pattern from a 2x2 system to this new situation, it's going to be helpful if we can picture the identity matrix for a 3x3 system. So you've got the ones on the diagonal, and what we do is we follow the same pattern that we did for a 2x2. First, we get the first one on the diagonal, and then we're going to get these zeros. So when we did a 2x2 system, we only had 1 0 to get. Now we're going to have to get 2. Then we're going to go to the next one in the diagonal, and then we're going to have to get the 2 zeros on either side of it. And then last, we're going to get the last one on the diagonal and then get the 2 zeros above it. So that's the pattern that we use as we do the Gaussian elimination. Go for the ones on the diagonals and then get the zeros that are above and below that diagonal. Okay, so I'm going to go ahead and start with this system. So I can write my augmented matrix from these equations. And the very first thing I have to do is get that first one in the beginning spot on the diagonal. And I do have a 1 in the second row. And so I'm going to go ahead and take the second row and just rewrite it in the first row. That way I don't have to multiply anything. I can just switch it out. So I'm going to say that row 2 becomes row 1. And then I'm going to take row 2 becomes row 1, and I'm going to take row 1 and move it to row 2. Row 1 becomes row 2. So 2, negative 1, 1, and then 1. Okay? And row 3 is going to stay row 3. Okay, so this is what we have so far. Next, now that I have the 1 in the correct position, I have to get zeros in each of the spots below it. So to deal with row 2, to get a 0 here, I need a negative 2. So I'm going to take the first row and multiply by negative 2. 1 times negative 2 is negative 2, negative 2, positive 4, negative 10. And then I'm going to add it to row 2. 2, negative 1, 1, 1. And all of these are going to be written as my row 2. Okay, so I took negative 2 times row 1. I added it to row 2, and that became my new row 2. All right, now for row 3, to get a 0 right here, I need a negative 3. So I'm going to take row 1, I'm going to multiply it by negative 3. Negative 3, negative 3, positive 6, negative 15. I'm going to add it to row 3. Negative 3 times row 1 added to row 3 becomes row 3. Okay, so 0, negative 4, 5, negative 7, and we didn't adjust row 1. We just used it to help us with the other rows. So I'm just going to copy row 1 there. So now our first column is ready. Moving on to the second column. I need to have a 1 in this position in the diagonal. So currently I have a negative 3 there. I need to multiply that entire row by the reciprocal. So row 2 is going to be multiplied by a negative 1/3. So negative 1/3 times row 2 is going to become row 2. So 0, positive 1, negative 5/3, positive 3. Okay, and then row 1 and 3 are going to stay exactly the same. 1, 1, negative 2, 5, 0, negative 4, 5, negative 7. Okay, so that's the second one in my diagonal. Now the numbers above and below that need to become zeros. So for this above to become a 0, that 1 just needs to be a negative 1. So I'm going to take this entire row and multiply it by a negative and then add them together. So 0, -1, positive 5/3, -3. And I'm adding that to row 1. So 1, 0. I'm going to come back to my fraction in a second. Okay. So this is 5/3. -2 would be -6/3. 5/3 and -6/3 is -1/3. Okay, so what I did is I took the negative version of row 2, I added it to row 1, and it's becoming row 1. Okay. Next, I need this -4 to become a 0. -4 is going to become a 0 if I have a +4. So I'm going to take this row, row 2, and multiply it by +4. So that gives me 0, +4, -20, -5/3 times a +4 would be -20/3. And then 3 times 4 is 12. Okay, and I'm going to add row 3. Zero, 0, come back to the fraction, 5. Okay. -20/3. 5 in terms of thirds would be 15/3. So -20/3 plus 15/3 is -5/3. Okay, so this becomes row 3. So what we did is we did 4 times row 2 plus row 3, and that became row 3. Okay, so 0, 0, -5/3, 5. Row 2 was correct from the step before, so it didn't need to change. Okay, so the first column is good, the second column is good. Now we need to fix the third column, and we're going to do that by getting a 1 in this position on the diagonal, and we do that by multiplying by the reciprocal. So -5/3 is what we have. We're going to multiply that by -3/5. That entire row is going to multiply by -3/5. So -3/5 times R3 is going to switch out the third row. So 0, 0. -5/3 times -3/5 is 1. 5 times -3/5. The 5s would cancel. I just get -3. So that's a lot better than it looked. Okay, so I'm going to copy down the other two rows. 0, 1, -5/3, 3, 1, 0, -1/3, 2. Okay, my next step is to get zeros in both of these positions. So right here, I have a -5/3, so I need a +5/3. So I'm going to do +5/3 times row 3, and I'm going to add it to row 2. Okay, so +5/3 times row 3 is going to be 0, 0, 5/3. 5/3 times -3. The 3's cancel, and I get 5 times a negative, so that's -5. Okay, and now I'm going to add that to row 2. So 0, 1, negative 5/3, 3. And so this is becoming row 2. Becoming row 2. Okay. To get a 1, or sorry, not a 1, to get a 0 in this position, I need a positive 1/3. So I'm going to take this and multiply it by positive 1/3. So positive 1/3 times R3, and I'm going to add it to R1. So row 3 is 0, 0, times positive 1/3 is 1/3. Negative 3 times positive 1/3 is negative 1. And I'm adding that to row 1. So 1, 0, negative 1/3, and 2. And that becomes row 1. And then row 3 didn't need to change. So 0, 0, 1, negative 3. And now we can see our x, our y, and our z. So there's a 1 right here in that first position. That's why we can see the x here. X is 1. There's a 1 in the y position, and so y is negative 2. There's a 1 in the z position, so z is negative 3. So 1, negative 2, negative 3 is the single point where all 3 lines cross.